What's up, everybody? I mean, there's nobody right now, but soon there will be everybody. Okay, if you are watching this, we do have a viewer. Okay, if you're watching this, not live, if there is anybody watching this not live, we're gonna start at 1:35. It's currently 1:27, so you can do the math. Okay, and I will also put in the description a timestamp for when we actually will begin. Starting at 1:35. Okay. Sorry if it looks like I'm filming this on like a, I don't know, like a pancake or something. I don't know what the joke is. Not great lighting. I'll turn the light on. One viewer. Let's go. Let's go. 2 viewers. Let's go. Starting at 1:35. I'll wait for people. Wait for stragglers. Hopefully there are at least a couple, but it is what it is if not. Oh yeah, and if you like, I guess I kind of said it everywhere, but the problems, you can find a link to a Google Doc with the problems in the description. You can take a look at them. I'm not going to go over problems 20 and 22 just because I didn't really have time to review them, or I didn't fully solve them, but I will go over them later at a certain point. What time is it now? Okay. My work. Okay, let's begin. So, the Putnam competition is a notorious nationwide college math competition taken by around 4,500 undergraduates each year. The test consists of 12 problems split into two 6-problem sections, and each section takes 3 hours to complete. So do the math, okay? The whole exam takes 6 hours. It's pretty brutal. Now, even though this exam is taken by some of the best math students in the country, the median score out of 120 is usually 1 or 2 out of 120. So the exam is pretty brutal. But that's not to discourage you from taking it if you want to take it, because it is, it will really push you and challenge you. And that's kind of like part of the reason that that's the big reason I like doing these problems and like presenting these problems, because it really pushes me and challenges me to be a better problem solver. So if you are a student of the University of Pittsburgh, like myself, okay, the university has a Putnam seminar class, which is a 2-credit class. It doesn't really satisfy any math major requirements, but it is a great class, and I highly recommend you take it. Yeah, I'll just repeat that for the new viewer who came in. So if you're a University of Pittsburgh student, Pitt has a Putnam seminar class. It's 2 credits. It's offered every fall. And you prepare for You prepare for the exam and just go over really interesting problems. Now, in 2020, or I guess, so the 2020 Putnam exam was held this year, actually, this February, and in 2021, which is kind of funny. It was in an unofficial mode, but they still kind of released some results. And I'm glad to say I got within the top 500 nationwide, which is my goal. But unfortunately, I was the only student in the entire university to take this exam. Okay, so please, I highly encourage, if you're a University of Pittsburgh student, I highly encourage you to take this exam. It's, I know it's kind of intimidating, but that's like the whole point, right? The whole point is kind of just diving into the belly of the beast. Okay, just gotta go for it. All right, enough about that. So these problems are from this book called Putnam and Beyond. It's this massive, like, how long is it? 800-page book of like 1,000 problems, and all of them, I mean, not all of them, but like pretty much all of them are very difficult and very challenging. I highly recommend you get this book if you want to prepare, if you just want to become a better problem solver. Like I said, the problems are very hard, so like I'm warning you, but the challenge is obviously healthy, and obviously I wouldn't know, but reportedly it's also good if you're planning on going to graduate level math. It's also good for you to go through some of the problems in this book to prepare for that. Now, this stream, so on my YouTube channel, I've done previous streams where I really dove into like one problem, maybe 2 problems for an entire hour or an hour or longer. And I really went over the big ideas, and I really broke it down and everything like that. Now, this stream, so this stream is going to be more like, I'm going to go through the problems a little more quickly. I'm not going to really break everything down, go through a ton of big ideas. This stream is more about like practice and just showing different techniques and methods. Because, as much as you can talk about, it's very important to really dissect problems and really go in depth. But as much as you talk about like problem solving strategies and like, and like as much as you talk about these big ideas, you really need to put in the practice to get the experience to be able to implement them effectively. So like, it's kind of, when you want to become a better problem solver, it's review is very important, and really digging deep is important, but also just straight up, just practice is important. That's not to say though, like I will still go through a lot of useful tips and tricks. I don't want to classify them as tricks. That makes them seem like cheap. They're like methods and strategies. Okay, there we go. And they hopefully are useful. Like I said, I'm cutting problems 20 and 22 just because I did have the time. I just didn't use the time well. So I didn't get to go over those in the book. Now, and I'm going to be going over my solutions. So there are solutions in the book. I didn't really look over them. Like I said, kind of, I was gonna, but like, you know how it is. Okay, I just kind of I procrastinated a little bit. So I'm just gonna be going over my solutions. My solutions are still, I think, pretty good though. Now, first, an overview of math induction. Now, I know, like, you might already know what math induction is, but I think it's still good to go over, and I'm going to go over my notation for it and why I think my notation is superior. Okay, it's not my notation. It's a very general notation, but it's I think it's a really good notation. So what you do, okay, let me think of like an easy math induction statement. It's like a common one. Okay, so a common one could be like, this isn't like something that's really good. All right, so what you do is you let P of n equal like a statement. Okay, I'll explain, I know my glare is terrible, but like it is what it is. I'll explain what this means later. So I'll use the statement 1 plus 1 over 2 to the 1 plus 1 over 2 squared plus 1 over 2 to the n equal to 1 minus 1 over 2 to the n. Okay. So what's going on here is, and I guess I define this, it doesn't really matter. So this P of n, it's actually, it's a function which takes n as an input and its output is true or false. So it's a true or false logical statement. And so that logical statement is the statement that 1 plus 1 over 2 to the 1 blah, 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 equals 1 minus 1 over 2 to the n. If instead I made, if you let P equal 1 equals 2, right? Then P is false, right? It's false. So the idea is, with math induction, is that if you can prove P of 1 is true, and you can prove that assuming P of k plus 1 is true, then P of n is true for all n in n, all natural numbers. I like this structure a lot because it's very general. Like I can write, I don't have to write an equation in here. I can write basically whatever I want in this little brackets, right? Any kind of statement I want, and I can still follow this basic structure. And it's really good for, it's just good for efficiency and everything. So, and then I won't go through the proof of this. I kind of just made it up on the spot, but maybe that's a little bit of a homework problem. No, I'm just kidding. Don't have to do homework. But maybe if you're, curious, you can go through the statement here. I guess I'll overview how I would do it. So first, so you say P of 1 equals, so you plug in n equal to 1. And that's 1 plus 1 over 2 to the 1 equals 1 minus 1 over 2 to the 1. So this is in brackets. This logical statement, it's logically equivalent to the logical statement. Wait up. Hold up. I messed that up. I meant to put, this 1 should not be here. Sorry about that. Okay. This is equal to this logical statement. 1 over 2 to the 1 equals 1 minus 1 over 2 to the 1. And that's equal to the logical statement 1 over 2 equals 1 over 2. And that is, well, true by the definition of equality, if you want to be super formal about it. So P of 1 is true. Okay. And then you assume P of k is true. And then you set out to prove that P of k plus 1 is true. And that kind of goes, I will demonstrate that using the examples, using the problems that I'm going to go over. Okay, I hope that makes sense. I think I will repeatedly use this structure, so it will become very familiar. Now, without further ado, let's get into the problems. So the first problem, let me pull it up. This problem is a classic induction problem, okay? You got this big fat sum, and it's dependent on n, and it's just ripe for induction, okay? So we're gonna go ahead and do it. Now, I will say that this problem, it's not. Now again, like this is all relative, of course. It's not too difficult. It's all relative. But you definitely could go about it in a very inefficient way. Like there's certain things that you can, certain simplifications you can make that can really make your life a lot easier. So this is problem 11. Now, problem 11 is the statement 1 over n plus 1 plus 1 over n plus 2, and you sum up to 1 over 2n. And then that's, you want to show that that's equal to 1 minus a half plus a third minus a fourth, and plus 1 over 2n minus 1 minus 1 over 2n. Okay. Now, what I'm going to do to make a lot of the, this is a lot to write out. Okay. Like every time you're trying to make it, like every time you're trying to advance a step in the proof, you just, writing all of this out all the time is super, it gets very slow and tiresome. So what I'm going to do to simplify my life here is I'm going to let L of n be the left side sum, okay, which I can define by so I equal k equal to 1. I guess I'll use I. The reason I'm using I is because I plan to use k. I plan to assume p of k. So I'm just trying to be a little cleaner here. I equal to 1 up to n of 1 over n plus I. And then R of n, I'm going to let equal to the sum. All right, this one got some alternating things going on. This would be sum from I equal to 1, or sum of I equal to 1 to 2n, and then it's going to be 1 over I. So it'll be not quite like a 1 over I. There'll be a negative 1 to the I plus 1. So the negative 1 to the I plus 1 over I. The reason, like the way you figure out this whole I plus 1 thing is because negative 1 is positive. It's 1 for even values of the power and odd for odd values, or negative for odd values of the power. So here we have a negative for the even values and a positive for the odd values. So we need to add 1 or subtract 1 to this thing up here so that we offset it correctly. Okay, so I'm letting L of n and R of n equal the left side and the right side. And what I want to show is that L of n equals R of n. And that's much nicer, much easier to say than showing blah, blah, equals blah, blah, equals all that. Okay? All right. Now, okay. So if you were proving this, if you're writing the full proof, you say let L of n equals this, let R of n equal that. And then you continue. Man, third person keeps joining and leaving, keeps toying with my feelings like that. Okay. So P of n is the true or false logical statement, which is equivalent, which is that L of n equals R of n. Now, first, P of 1. Okay. So P of 1 is equal to the statement that, so it would be 1 over 1 plus 1, which is 2. And then 1 over 2 times 1 is still 1 over 2. So there's only one term on the left side. And this is equal to 1 minus a half, right? And then that's equal to the statement a half equals a half. What a coincidence. That's like the same as what we had before. And that is true. Boom. So P of 1 is true. Easy money. Easy money. Now we're going to assume P of k is true. So we're going to assume L of k equals R of k. And this is like, again, this is kind of a classic induction problem. The goal is going to be to express L of k plus 1 and R of k plus 1, we want to express them in terms of L of k and R of k. We want to find some kind of recurrence so that we're able to apply the inductive hypothesis in order to prove the inductive step. So let me just go through what I mean. Now, L of k plus 1 equals, so like, I'm not going to use the summation notation. That's just to be a little formal about it. Like, it's better to think about it in the expanded form. So L of k plus 1 is 1 over k plus 2 plus 1 over k plus 3 plus 1 over 2k plus 1 over 2k plus 1 plus 1 over 2k plus 2, because this is 2 times k plus 1. Now, this is equal to, there's a lot of terms in common with L of k. Importantly, though, we are missing 1 over k plus 1. And we've added 1 over 2k plus 1 and 1 over 2k plus 2. Okay. So that's L of k plus 1 in terms of L of k. You have these terms that are added. Next, let's look at R of k. So R of k plus 1, R of k plus 1, equals 1 minus a half plus a third plus 1 over 2k, no, minus 1 over 2k, plus 1 over 2k plus 1 minus 1 over 2k plus 2. And this is equal to, so this whole thing here is just R of k. Again, I'm sorry if my camera's pretty crappy, but I mean, I recommend, if you really want to get the most out of this, I mean, if you're just watching it, just to watch it, that's totally cool. But writing out kind of like what I'm writing, like taking notes, I mean, if you want to, I would recommend you do that if you want to have a stick with her. But it's not necessary. So R of k plus these two extra terms, 1 over 2k plus 1 minus 1 over 2k plus 2. Now, what we'd like to show is that L of k plus 1 equals R of k plus 1, and we know that L of k equals R of k. So it suffices to show that these extra terms equal these extra terms, right? Yeah. And not only, so this is a distinction that will become important later. Not only is it sufficient to show that these terms equal these terms, so if we do that, then we've proven it, but it also must be true. 100%, these extra terms must equal these extra terms in order for L of n to equal R of n for all n, okay? Because otherwise L of k equals R of k, and then when you take the inductive step, the L of k and R of k plus 1 will become offset because those extra terms aren't equal. So this must be true, 100%. So we know that we're quote unquote safe. I will explain what that means later with a later problem. Okay, so what we want to show, I know my board is tiny, so kind of being a little crammed. So WTS, this is a thing that I highly recommend you use when you're doing problems, want to show. It allows you to distinguish between statements you already know are true and statements that you want to prove later. Want to show that 1 over 2k, well, I guess I'll use left, the extra terms on the left equal the extra terms on the right. Minus 1 over k plus 1 plus 1 over 2k plus 1 plus 1 over 2k plus 2 equals 1 over 2k plus 1 minus 1 over 2k plus 2. Okay, I know there's a lot going on here, but all right. And then this here, like if you just look at this equation, right, there's 1 over 2k plus 1 and 1 over 2k plus 1 will cancel. And again, it's hard to see, but actually, you know what, screw it, I'll write it bigger. It was hard to see. Okay, so you want to show that minus 1 over k plus 1 plus 1 over 2k plus 1 plus 1 over 2k plus 2 equals 1 over 2k plus 1 minus 1 over 2k plus 2. Okay? And what you can notice is that these terms cancel. And you want to show that minus 1 over k plus 1, or I guess if you just do the rearranging, right? 1 over 2k plus 2 is half of 1 over k plus 1. So this like simplifies pretty nicely. So, you get like, I'm going to add the 1 over k plus 1 to the right side and then add this to this side. So we get 2 over 2k plus 2 equals 1 over k plus 1. And, 1 over k plus 1 equals 1 over k plus 1. So this is true. Okay. So that was our work for this problem. Oh, what's up, Jake? No, it's fine. It's fine. That was our work for this problem. Now, if you were actually proving the problem, what we would do is, so there's a couple ways we could go about it. The way you prove it, in general, the way you prove problems is backwards from how you work them through. So what you would do, for example, you would begin by proving that the extra terms equal each other, right? You begin by proving that, and then you use that like to prove that L of k plus 1 equals R of k plus 1. It's just cleaner when you prove it that way. Although, like, you would never. The thing is, you can't work that way because you don't know it's going to end up looking like this. So I'll just give a really quick proof outline. Okay, so use the whole. So you'd say something like, now we already showed the base case. So then we assume P of k, okay, which is the logical statement, the true-false logical statement, that L of k equals R of k. So you assume that, and I guess, and then you would show that like the extra terms are equal to each other. So you show one of this plus this. 1 over 2k plus 1 minus 1 over 2k plus 2. You show that, and then you say, okay, well, if this is true and this is true, then L of k plus this is equal to R of k plus this, and then, but this is equal to L of k plus 1, and this is equal to R of k plus 1. So, boom. Bingo, bango, bongo. You got the proof. All right. I'm not going to belabor that one too much, though. All right, next problem. Oh my, we've already been going for a while. Okay, so the next problem, problem 12, prove that. So prove that the absolute value of the sine of nx is less than or equal to n times the absolute value of sine x, where x could be any like real number. Okay. Now, from an intuitive perspective, the way you can think about why this is true is because, like, as you increase n, this left side is still confined to be between -1 and 1, right? Because it's a sign of a number. But this right side is allowed, as you increase n, this right side can grow without bound. So if you can show that, like, the intuitive idea is that if you can show that this is true for like the earlier stages, right, then as you increase n, it only becomes increasingly like less true, right? This term will run away from this term. Now let me pull out my work for this. Okay. Oh my, where is it at? Okay, yeah. Now, so P of n we say is equal to this true or false logical statement. Then P of 1 would be that the absolute value of sine times 1x is less than or equal to 1 times sine x. Absolute value of sine x. Okay. Base case, usually cake. All right. Was cake. And then we assume P of k. In other words, we're assuming that the sine kx is less than or equal to k times the absolute value of sine x. Sorry if I'm omitting some absolute values. And we want to show, again, this is where the WTS comes in. And like I said, this whole want to show thing, you would never write this actually in a proof. This is always when you're doing work, okay? Because in the proof, you just show it, right? You want to show that sine of k plus 1x is less than or equal to k plus 1 sine x. Okay. So what we're going to do, this is, again, common induction strategy, is we want to somehow connect this to that, right? We want to express this in terms of that so that we can apply the inductive hypothesis and prove the statement. So one way we can do that is, so you have sine of k plus 1x and sine of kx. We can use the sum addition formula in order to get a sine of kx over here. Okay, and then apply this, and hopefully things will come out nicely. We'll see. So the sine of k plus 1, and I'm maintaining the absolute values, obviously. It's equal to, now we're going to use the sine addition formula. So this is like the sine of kx plus x. And this is equal to sine kx cosine x plus sine x cosine kx. And now, so for inequalities, so we want to show eventually that this is less than something. Okay, we want to show that this is less than or equal to k plus 1 times sine x. So we want to somehow find a way to show that this is less than or equal to something else. Okay, because if you want to show that a is less than b, you want to show that a is less than this is less than this and less than this and less is less than b, right? It's not helpful if you say, oh, okay, I want to show a is less than b, then I'm going to show that a is less than this, but this is greater than this. That completely screws up the entire chain. So you're always looking for, make sure you know how you want your chain to, which direction you want your chain to go. Now, so we have this sum of two terms and an absolute value. We want to show that it's less than or equal to something. Okay, and so the answer is almost always triangle inequality. Triangle inequality is that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. If you just the best way to, well, there's many ways you can think about it. A good way to think about it is just test cases, right? But it also works for complex numbers, which is interesting. So this is less than or equal to the So the absolute value of sine of kx. Now, in the absolute value of sine kx cosine x, okay, this term, absolute value of a times b is equal to the absolute value of a times the absolute value of b. These are just certain things that are good to know for simplifications. Absolute values behave. I think people underestimate how confusing they can become. It seems like such a basic function, but I think because it's really like a piecewise function if you think about it, right? If x is negative, then you flip the sign, and then if it's positive or 0, you maintain the sign. So because it's like a piecewise function, I think that makes it a lot more complicated. It makes it there's a lot of complicated things that come with it, like complicated identities, and you always have to do casework because at its heart it's a piecewise function. So never underestimate the absolute value. Whenever you have an absolute value in a problem, never underestimate that. It can become kind of confusing, and make sure you're patient with yourself. Okay. So simplify now. And so next, what do we want to do? So again, remember, got to keep your eye on the prize. Okay, eyes on the prize. We want to show that this is less than or equal to k plus 1 times the absolute value of sine x. So here we have the sine kx. We know that this is less than or equal to k times the absolute value of sine x. And we can be really confident we're going to use that. We're going to make that simplification because like that's the inductive hypothesis. We're going to have to use it somewhere, and like it seems pretty clear like we're going to have to use it there. There's not much else we should do. And the absolute value of cosine x, I mean, this is pretty fine by itself. We don't really need to do anything to this, right? Because k plus 1 times the absolute value of sine x, that's equal to k sine x plus absolute value of sine x. So like what we can do is we can note that the absolute value of cosine x is less than or equal to 1 so that we don't like disturb this term. I guess I could write that absolute value of 1, but like, I don't know, it doesn't seem that necessary. And in this term, so we need another sine x term, right? And cosine of kx is also less than or equal to 1, right? And then this is equal to k plus 1 times the absolute value of sine x. And so we've shown that sine of k plus 1x is less than or equal to k plus 1 times the sine of x, the absolute values. Yeah, so this problem, there's some tricky things navigating it. Inequalities can become a bit tricky. In general, like I said, make sure that you keep you keep your eye on the prize, right? You want to always consider like what you're aiming for, because with inequalities, there's a lot of different simplifications you can make, and picking the right ones is all about analyzing where you want to go, and also analyzing like also just through experience what is useful. It's kind of like it's hard for me to explain. Like, I mean, if you've never used a triangle inequality before, it's hard for me to really like explain how you could think to use triangle inequality here. But like, if you use it a lot, like when I did this problem and I saw this, I just immediately like, okay, triangle inequality, because it's kind of a thing that comes up a lot. So experience is also very, very important. Okay. All right. Next one, another tricky one. I'm gonna get some water. So this one is trickier, okay? For this one big reason that comes up a lot in inequalities, and can really be a confusing point. It was a huge point of confusion for me, and then I realized kind of what I was doing wrong. Okay, I think I wrote the full proof of this because it was like kind of hard. Okay. Oh yeah, but how do I go about? Okay. Yeah. Okay. So I'm gonna go through my work for when I first tried this problem, and this is very like even if I was like some master mathematician, right? I would like to think I'd still kind of approach it this way at first. But it's a bit problematic, and why it's problematic is very subtle. Actually, you should see if you can catch why it's problematic. Okay, so we want to show 13. So we want to prove that the absolute value of sine of x1 plus up to the absolute value of sine of xn plus the absolute value of the cosine, the glare is pretty bad, of x1 plus x2 plus xn is greater than or equal to 1. And this has to be true for all real numbers x1, like any set or sequence of numbers x1 to xn, and any natural number n. Okay, so this is another inequality. Now, so I'm gonna kind of tackle this, and again, I'm just gonna go through the work. So like, well, first I suppose we should do p of 1. Okay, so again, p of n we let equal this statement, and p of 1 is equal to the statement that the absolute value of sine of x1 plus the absolute value of cosine of x1 is greater than or equal to 1. Now this one here, this isn't like, I mean, this base case is not completely obvious how to do on its face. Now, intuitively, the reason that this is true, how do I explain this? I mean, if you plug in values, if you just plug in values, then you can see like kind of why this is true, like kind of, okay? If you plug in like x1 equal to 0, right, then this term is 0, this term is 1. So obviously, like on the unit circle at like the intercepts, obviously, you know, it'll just be equal to, this will be equal to 1. I say obviously, I should not say obviously. It's not obvious. I've just worked with this problem a lot, so I've already figured that out. And then you know, if you plug in like x1 equal to pi over 4, then this is equal to the square root of 2 over 2 plus the square root of 2 over 2, and that's the square root of 2, which is also greater than or equal to 1. And like I said, if you just plug in other values, you'll see that this is always greater than or equal to 1. Now, to show this, the way I would think about this is, where else do I see like a sine of a number plus a cosine of a number and a 1? Okay, where do I see some equation? Okay, it's very like nebulous. Okay, so some equation, and it's got going on. All right, my equation. I don't actually think of it like a circle or anything. This is just my way to look at it or to demonstrate it. So you got like a sine of x1, or just a sine of x, a cosine of x, and a 1 going on in that equation. There's also a plus sign going on somewhere. Okay, where do you see this? The answer is in sine squared of x plus cosine squared of x equals 1. Okay, that's the first thing that I was drawn to. Okay. Now, and so that's what we know. So we know, and furthermore, what's useful about this is that the sine squared of x is equal to the absolute value of sine x squared, right? Because when you square something, absolute values don't matter. So we know that the sine of x1 squared plus the cosine of x1 squared equals 1. And, you know, we can make these absolute values and it won't actually change anything. Okay. Okay, we want to relate this to this. So how do we go from this equation? So like what I'd ask is like, what's the difference between these two equations? Like how can I go from here to here? The answer is these squared terms going on, right? So how do I get squared terms going on in this equation? The answer is like, let's square it. Okay. So what I'm going to do is, and just the left side. Okay, just the left side. I'm going to square this. So I want to show that. So furthermore, if I can show that this squared is greater than or equal to this squared, then this will be greater than or equal to this. A squared greater than or equal to b squared implies a is greater than or equal to b if a and b are positive, right? So I want to show that, and so I'm going to square this. Now I'm just going to FOIL it out just immediately, okay? So sine of x1 squared plus 2 sine of x1 cosine of x1 plus cosine of x1 squared is greater than or equal to 1. Sorry if that's really bad. Okay, so I want to show that. And what I know, so let me erase. Oh no. Oh, no, I can erase this. So what I know is that this plus this, these two terms equal 1. So instead, I can simplify this. I can say I want to show that 1 plus, and then this extra term, is greater than or equal to 1. But that's true because this term is always non-negative. right? 1 plus the absolute value of something is always going to be greater than or equal to 1. And so I've kind of reached like the bottom of the barrel. And then when I actually prove that P of 1, I would start from this statement, right? I guess you would start from, if you really wanted to be like all the way at the bottom, you would start with like the absolute value of 2 sine x1 cosine x1 is greater than or equal to 1. Okay. So the absolute value of, 0, because the absolute value of anything is greater than or equal to 0. And then you simplify this out, you add 1 to both sides, then you add these squared terms, then you factor, take the square root, and you can show P of 1. All right. Enough of the base case. Now, so what now I'm going to assume P of k, and I want to show P of k plus 1. To simplify my math, I'm going to do a similar thing with problem 11, where I let L of k equal the entire left-hand side. So I'm going to let, or I guess L of n. So L of n is going to equal sine x1 plus plus sine of xn plus the cosine. Man, why am my handwriting getting so bad? I gotta slow down. So sine of x1 okay, so I'm going to let L of n be that, and I want to show that L of n is always greater than or equal to 1 for any value of n. Okay, so L of k, so what I'm going to do, classic induction, I'm going to express L of k plus 1 in terms of L of k, and use the fact that L of k is greater than or equal to 1 to show that L of k plus 1 is greater than or equal to 1, right? So L of k plus 1. Now, L of k plus 1, you'll have all of the same terms as L of k, except you have L of k, except you get an extra sine of absolute value of sine of xk plus 1. And this cosine term is going to have an extra xk plus 1 in it. So what I'm going to do to simplify my logic even more is I'm going to let, I guess I should have, again, this is just like how you work through a problem, so it can be a little messy. This isn't the actual proof. So I'm going to let theta equal x1 up to xk, okay? Or I could let it be like theta sub k, whatever. So I'm going to let theta equal that. And so this here, L of k plus 1, L of k plus 1 will have a cosine of theta plus xk plus 1 term, but it's not going to have the cosine of theta term. Okay. Now, one of the reasons that I did this theta thing is because if you really like think about it, xk, x1, like all these, they can be whatever you want. They can be any real number. So this theta here, it can be anything. It could be any angle whatsoever. So like you don't have to think of it like, oh, it's the sum of all these different numbers. No, you can just think of it as one number that could be anything, right? Okay. Now we know that L of k is greater than or equal to 1. Okay. Sorry, my work's getting a little messy. So we know that L of k is greater than or equal to 1. And we want to show that L of k plus 1 is greater than or equal to 1. Okay. So what we can do is show, let me erase and rewrite this whole thing. So we know L of k is greater than or equal to 1. We want to show that L of k plus 1, which equals L of k plus the sine of xk plus the cosine of theta plus xk, or xk plus 1. Crap, I'm rushing. sine of xk plus 1 plus the cosine of theta plus xk plus 1 minus the cosine of theta is greater than or equal to 1. We know this, we want to show this. So what we can do is show, instead, like we could say, okay, we want to show that all of these extra terms are greater than or equal to 0. Okay? Because if you have like, if you want to show a is greater than 1, and it's a bad example. So you want to show like, let's say a equals b plus c, okay? And you want to show that a is bigger than 1. You know that b is bigger than 1. So you want to show that c is bigger than 0, right? You want to show that c is not negative, because then if that's true, then you're good, right? So we want to show that these extra terms, that these terms are greater than or equal to 0. Okay. And if we can show that, this is bigger than 0, we know that this is bigger than 1. So something bigger than 1 plus something bigger than 0 is bigger than 1. Okay. Enough of that. Now, so what we can do, like, this is a pretty confusing equation going on. Okay. This is no walk in the park. What we can do is, so we could do a couple simplifications. I'll save you the time though. So the first thing I do is I'd expand this out. Okay. I would expand this out using the cosine addition formula. I might want to use some triangle inequality as well in order to simplify things a bit further and kind of follow it down. I'm going to save you the time. It doesn't work. Okay. And when it doesn't work, and then what you always want to do whenever you get stuck is you want to take a step back. You want to think about, like, is there a different thing is there a different path I can take with this, right? So you take a step back to your closest step, and if you get stuck, then you continually take step backs until like the first step you took, right? Because you took like it's like when you're solving a math problem, there's many different. You start with the first thing you think of, right? No, you start at the very beginning. There's many different paths you can take, right? And it's like a tree of paths you can take, and a couple of these paths will lead to the solution. The vast majority of them will not. And every time you make a simplification or you take a step, you make an algebraic step. Every time you take a step, you are branching off into a new path. So there's like tons of different paths. And whenever you get stuck, whenever you reach a dead end, that could be like one of those paths that doesn't work. So you want to take a step back up the tree to the last statement, the parent node, if you know CS. And then you want to think about what are the possible paths I could take from there. And if that doesn't work, then you backtrack again and you continually backtrack. When you're actually solving a hard problem, thank you, Jake. When you're actually solving a hard problem, even the most experienced, like even the best mathematicians in the world, okay, it's very hard to get the right path on the first try. There's a lot of times you have to backtrack. And even if you do, like, you're not guaranteed to find the solution at all. You have to be patient. It's a tricky thing. So yeah, like I said, you get stuck when you try this. Okay, so what else can we do here? Now, a good kind of thing that you can do when you're just kind of bogging yourself down in the algebra is you can think about, okay, why is this intuitively true? You try to gain an intuitive understanding of this equation or inequality. And the best way to do that is just to kind of plug in values, just play around with it and see what's going on. So let's see. Okay, so if we plug in xk plus 1 equal to 0, super easy one, okay? Xk plus 1 equal to 0. This term will be 0. This is cosine of theta. This is cosine of theta. Cosine theta minus cosine theta with absolute values. That's greater than or equal to 0. Okay, it's true. Okay. Next, what if we plug in, let's see, what else did I try plugging in? Okay, what if we plug in, oh yeah, one thing, when you plug in values, you also, to convince yourself it's true, you try to make it false. You try to think of how can I make this false? Like, where is the weakest point in this? And that allows you to figure out like why it's so strong. So, I gotta think of okay, so let's say I plug in, okay, here's a good one. Let's say I plug in xk plus 1 equal to pi. The reason I'm doing that is so that I can get rid of this term, make my life a little easier. So xk plus 1 equals pi. So I want to show the cosine of theta plus pi, the absolute value, blah, minus the absolute value of cosine theta is greater than or equal to 1. And that's also true because, you know, if you imagine the unit circle, cosine of theta plus pi is equal to negative cosine theta. So they have the same, 0, same absolute value. Okay. Let's see. Let's say I plug in, I'm trying to figure out where I can do here. Let me look at, okay, let's say I plug in xk plus 1 equal to pi, let's say I plug in xk plus 1 equal to pi over 4, okay? So then this would be square root of 2 over 2. And so we want to show that, oh God, let me look at my work. I'm kind of winging this a little bit. I got a lot of work pages. So okay. I think there's a way that I can make this false. Yeah, okay, so what I'm going to do is let theta equal minus pi over 2. Wait a sec. I'm going to let okay, I can't think of an example. I apologize. Basically, this statement here is not always true. Okay, I can't think of an example right now of why, but I can't remember what exactly I did. But when there is certain values that you can plug in here, and this statement here is actually false. Okay, so that was I was trying to get there, but I forget exactly how I did. But I'll cut to the chase. This statement here is false, or at least when you simplify this statement, you get when you try to simplify it, right? You eventually simplify it down to a false statement. Now the reason is very subtle. Okay, so we want to show. Let's see. We want to show that L of k plus 1 is greater than or equal to 1. Okay, we know. Wait, let me get my eraser. We want to show that L of k plus 1 is greater than or equal to 1. We know that L of k plus 1 is equal to L of k plus, and I'm just going to say this is like big E for extra terms. And we want to show that this is greater than or equal to 1. We know L of k is greater than or equal to 1. Okay, but it's not, oh my God, okay. But it's not necessarily the case that E is greater than or equal to 0, okay? So for example, like let's say L of k plus 1 was equal to 1.5, and L of k was equal to 1.3, okay? Then L of k plus 1, or wait, no, reverse that. Then L of k plus 1 is equal to 1.5, and then plus E, which is minus 0.2, right? And it's greater than or equal to 1, okay? So like, just because A is bigger than 1 and B is bigger than 1, or let's say, can I write? Yeah. Let's say A equals B plus C. Then just because B, if you want to show that A is bigger than 1, just because B is, if A is bigger than 1 and B is bigger than 1, that doesn't mean that C is bigger than 0, because A could be like 5 and B could be like 3. Okay? So this is a weird thing with inequalities. With inequalities, like, you can't do the same with equations if like the left side of, if like you have left side bigger than right side and of one equation and left side bigger than right side of a second equation, that doesn't mean that the left side of the first minus the left side of the second is bigger than the right side of the first minus the right side of the second. You can't do those same simplifications as you can with equations. You have to be really careful that you're not making one of these like logical errors. I apologize that I explained it kind of poorly because I couldn't find the correct example, but the whole gist of it is like, we don't need to show that E is bigger than 0. If we could show that E is bigger than 0, then we would have proven the statement, right? But it doesn't have to be the case, okay? It's a sufficient condition, but it's not necessary. And so you have to be very careful that you make this distinction in your head, because like when I was first solving this problem, I did not think about this. So I was setting out, basically I was setting out to prove that E was like bigger than 0. I was setting out to prove this statement that was actually false, right? Which is like total waste of time. It just wasn't true. And but the thing is, it doesn't have to be true for the statement to be true. Another way you can think about this is that if E is bigger than 0, that would tell us that L of 2 is bigger than L of 1, and L of 3 is bigger than L of 2, and L of 4 is bigger than L of 3. So it assumes that the left side is always an increasing function, okay? But it doesn't have to be increasing. We just have to show that it's always bigger than 1. It could oscillate and still be bigger than 1, right? So we made like this inherent assumption that was very hard to detect, and it kind of screwed our process. Okay. So the next question is, okay, so what do we do then? Okay, how else can we show this statement? Now, the answer, and let me sift through all my work. The answer is to stick as closely to the original inductive statement, or to the original inequality as possible. Okay, so when we try to prove that E was bigger than 0, right? That was sufficient but not necessary. It was like an auxiliary statement that could have helped us. Now, the way that we make sure that whatever we're trying to prove must be true is we stick as close as possible to like the original statement. We don't try to prove these auxiliary statements, right? We just stick with what's going on. So we want to show that, see, this is my proof of this. So, and my work is over here. Okay, so let's backtrack and let's look back at our original sum. L of k plus 1 is sine of x1 up to sine of x sub k plus 1. And that plus the cosine of x1 plus up to xk plus 1. That is L of k plus 1. And we're going to try to do our best to not make any inequality type simplification. Well, no, that's not actually true. We're going to do our best to not mess with this too much. Okay. So this is going to be equal to, okay, yeah. And what we're going to do is let, so we're going to let, this will come up later, okay? We're going to let C, big C, equal the absolute value of the cosine of x1 up to xk. And we're going to let big S equal the absolute value of the sine of x1 up to xk. Okay, that will come up later. Okay, so okay, so this here is equal to the sine of, this is equal to the sine of x1. Oh my God, you guys are falling. I'm sorry about that. Okay, the sine of x1 plus up to the sine of xk plus the sine of xk plus 1. And this here will be, and then plus the cosine of x1 up to xk plus 1. Now, this here, we know that, so, yeah, okay. All right, yeah. And then this, so what we're going to do with this thing here is we're again going to do the cosine addition formula on this thing to express it in terms of the cosine of x1 up to xk, right? Because we still want to relate L of k plus 1 to L of k. So this equals the sine of x1 plus, and then the sine of xk plus 1. And then we're going to use cosine addition formula on this. We're going to split it x1 to xk and then xk plus 1. So this would be the absolute value of the cosine of x1 up to xk. So cosine minus sine, I believe. Yep. And I'm going to use the, well, I'm going to use the big C and the big S notation. I don't know where I put my eraser. Here it is. So you have the cosine of all those terms. That's going to be big C times cosine, so cosine of xk plus 1 minus then the big sine and then sine of xk plus 1. I mean, it's not actually a big whatever. All right. Next, what we're going to do is use we're going to use a form of triangle inequality on this. It's called the reverse triangle inequality, and it allows us to do something important. Again, what we want to we want to keep our eye on the prize. So what we want to do is we want to show eventually that this here is bigger than 1. Okay, that it's bigger than something. Okay, so if you look at the normal triangle inequality, it says that the absolute value of a plus b, a plus or minus b, the glare is terrible, but absolute value of a plus or minus b is less than or equal to the absolute value of a plus the absolute value of b. Okay, so like the when you split the terms, then that's going to be bigger than when you have them combined. The problem is here we have these terms combined, and we want to show that this is bigger than something. Okay, so we want to show that like c cosine of xk plus 1 minus s sine of xk plus 1 is bigger than or equal to something. But the thing is, the triangle inequality, like, we want to split the terms too because it helps the simplification. If we split the terms, then we only have this less than or equal to sign, not the greater than or equal to sign. So that breaks like the chain of inequality. As a result, what we can do is use something called the reverse triangle inequality, which allows us to show, like, do the other direction. The reverse triangle inequality says that the absolute value of A plus or minus B is greater than or equal to the absolute value of A minus the absolute value of B. Okay, the way you show this is, I guess I will use I'll use A minus, or I guess, yeah, I'll just use A minus B here. So the way that you show this, the reason is because the what you can do is think about the absolute value of A as equal to the absolute value of A plus B minus B, and that's equal to the absolute value, and that's going to be less than or equal to the absolute value. I guess A plus B. This could also be A minus B plus B. It doesn't matter. Okay. I'll use minus plus. This is going to be less than or equal to A minus B, the absolute value of A minus B plus the absolute value of B. So it's still the triangle inequality, right? But instead we've got this combined term on the right side now, on the greater than side. And so what we can do is subtract absolute value of B from both sides, and we get the absolute value of A minus B is greater than or equal to the absolute value of A minus the absolute value of B. And that you can also think of like intuitively or logically if you just kind of test cases. So we're going to use the reverse triangle inequality here to break this apart while still maintaining the correct chain of inequality. So the absolute value of, let me see it. Yeah, this problem is long. This is no joke. So this whole thing will be greater than or equal to, I know I'm kind of going up, but whole thing will be greater than or equal to, then the sign terms are still just kind of coming along for the ride. Wait, did I simplify that though? No. And then plus, then it's going to be absolute value of this minus absolute value of this. And once again, I'm going to split the terms with the absolute value, because you can do that. Okay. Okay. So next we can notice. Next we want to use the inductive step or the inductive hypothesis. So we know that that when we add the sine of x1 up to xk. Man, my handwriting I'm rushing a bit. It plus like this cosine term, absolute value big C, is greater than or equal to 1. So what we're going to do is we notice that we can move that absolute value of C to the other side, okay? And so that's useful because then we can take the sum of the first like k sine terms, we can replace it with this, okay? Because it's bigger than that. So we know that this here is greater than or equal to the 1 minus absolute value of C. Then we still have this extra sine of xk plus 1 term. And this is plus absolute value of C, and then absolute value of cosine xk plus 1 minus absolute value of S, absolute value of sine of xk plus 1. Now, the reason that this is different, this method is different than the one we did before, is because we haven't tried to set out any like auxiliary statement or anything. Like we've worked completely with like the initial form. We didn't make this any kind of assumptions about what the left-hand side is doing. We did make some simplifications using the triangle inequality that could potentially mess us up, but it's not really likely because that would be that would make the problem kind of a stupid problem if you couldn't simplify it this way. So we're just following this down. We're just following it down. We want to show that this is greater than or equal to 1. This whole thing is greater than or equal to 1. So, okay, let me write this out. Let me look at it. Remember it? Okay. So, I guess I don't have to erase it. We want to show that this whole thing is greater than or equal to 1. Oh my God. Greater than or equal to 1. So what we can do is, so we want to show, let me just write it out, okay? 1 minus, and then this whole thing is greater than or equal to 1, okay? This term. So what we can do is show that, and this is one of those things that this is a must be true. Okay, this is necessary and sufficient. If one, actually no, it's kind of not, but it's a simplification that we need to make. So yeah, minus absolute value of c plus sine of xk plus 1 plus c. Oh yeah. Absolute value of s, absolute value of sine of xk plus 1 is greater than or equal to 0. So we're showing that 1 plus this whole thing is greater than or equal to 1, so we can show that this is bigger than 0. Now, technically, this doesn't have to be true, right? We had the whole discussion about it. If 1 plus a number is bigger than 1, that number doesn't have to be bigger than 0, right? Because, wait. Yes, it does. Yes, it does. Right? If 1 plus x is bigger than 1, then x must be bigger than 0. Okay, yes. Never mind. Okay, now you simplify this, you can factor it, blah, 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 and I will save you time, and I'll just do it. So this simplifies to the statement. Dang, this problem is, this is a long boy. This simplifies down to sine of xk plus 1 times 1 minus s minus c. Oh, absolute value of s. Actually, wait. Let me make sure I'm skipping a couple steps. Yeah, so this would be sine of xk plus 1. Actually, I'm going to make a quick simplification. So I'm going to let alpha equal to x1 plus xk and beta equal to xk plus 1, just so that I can kind of think about these, and it's just a good simplification to make, so that I don't have all of these s's and c's and xk plus 1s. It's kind of gross. Let's just use alpha and beta. So this, when you simplify the statement, you do the math, it's just algebra, okay? You get sine of beta times 1 minus sine of alpha. Wait. Oh yeah. So you get sine of absolute value of sine of beta, absolute value of cosine of beta, plus cosine of alpha, absolute value of cosine of beta, minus, or I think that these are also absolute valued. Yeah. Absolute value of sine of alpha, absolute value of cosine of beta. We want to show that this is greater than or equal to 0. Okay, we're almost there, I promise. Almost there, I promise. Now this base case, this is bigger than or equal to 1. Okay, so we want to show that this is bigger than or equal to -1. Okay, so we already the details aren't super important. The idea is we already know how to bound this. We already know what this is this is bigger than or equal to 1. Okay, we don't really know anything about this, so we want to work with this term. Now this term here should look familiar. It's okay if it doesn't. It's, oh wait, hold up. This is a sign. Yeah. Now this term here looks a lot like the cosine addition formula. Okay? And if we can say that this is equal to the cosine of a number, then that must be bigger than or equal to -1. And we already know that this is bigger than or equal to 1, so this whole thing is bigger than or equal to 0. And so we've proven, we would be able to finally prove the statement. The thing is, there's all these absolute values that are flying around, and that makes it kind of annoying. Okay, so what we can do is so we got all these absolute values going around. It's pretty annoying. So after playing around with it, the easiest thing to do is to notice that so if alpha and beta were from 0 to pi over 2, okay, classic, that's like classic right triangle trigonometry going on. Okay, sine of alpha and sine and cosine are always positive, super nice and easy. Then all these absolute values go away, and you can simplify it to cosine of alpha plus beta, and then you can bound that. The problem is alpha and beta could be anything. So, but what you can do is, if alpha is, let's say 3 pi over 4. Okay, if alpha is 3 pi over 4, then if we pick alpha prime equal to pi over 4, then alpha and alpha prime, they have the same sine and cosine values, but alpha prime has the positive values of it. So for 3 pi over 4, the sine of 3 pi over 4 is positive square root of 2 over 2. The cosine is negative square root of 2 over 2. And for pi over 4, you get the positive versions of that. And for any angle that you any real number that you have, I guess anything in pi 0 to 2 pi, you can always no matter where you are in the unit circle, you can always pick a point in the first quadrant which has the same absolute value of sine and the same absolute value of cosine. So what we'll do is you define alpha prime and beta prime such that, and they're in 0 to pi over 2. Okay, such that the sine of alpha prime is equal to the absolute value of sine of alpha. The cosine of alpha prime equals the absolute value of the cosine of alpha. And you do the same for, the same is true of beta and beta prime. Okay? Then what that allows us to do is to totally strip away the absolute values, which were hindering us. And doing so, after making these simplifications with alpha and alpha prime, you get cosine of alpha prime, cosine of beta prime, minus sine of alpha prime, sine of beta prime. That's equal to cosine of alpha prime plus beta prime. And that will always be greater than or equal to -1. So because this is always greater than or equal to -1, and this is always greater than or equal to 1, this whole thing is always greater than or equal to 0. And if you backtracked all the way up, you would eventually finish this problem. You'd eventually prove this problem. Okay, I didn't expect that problem to take that long to explain. I don't know why I expected it to be any shorter though, because it's a long problem. A couple notes on the alpha prime beta prime thing. If you don't get that, I would you can if you want to be explicit, you can do casework. So you can think about what would happen if alpha was if one of the angles was in the first quadrant. If it's in the first quadrant, you just pick the same angle. Then if it's in the second, the third, and the fourth, you can do casework, and you can hopefully convince yourself that no matter what angle you're given, from 0 to 2 pi, you can always pick an angle between 0 and pi over 2 that has the same absolute value of sine and cosine values. Okay, now if you were to prove this, and I won't go through the proof, what you do is you start from the bottom, okay? Not like the Drake song, you just, never mind. You start from the bottom. So you would first prove that, you'd first demonstrate this inequality, okay? Using the same argument I just did. So you show this is P of 1, right? We already went through that. You'd show this, and then you'd show that this inequality holds true for any value of alpha and beta. Then you plug in alpha equal to x1 to xk, beta equal to xk plus 1, and you look at your work and you just go backwards in your work, and you eventually will be able to prove that P of k implies P of k plus 1 and prove the problem. Finish the problem. Okay. Wow. Yeah. That was a long one. as long as it seemed, a lot of this is not it's very long, but a lot of this is at each step comes kind of with experience, but knowing what simplifications to make and what would work well. And although it's long, it's algebraic, right? So there's not a lot of intuition you really need to use on a geometric level. You need to use intuition, algebraic intuition, but you don't need to be really conceptualizing, things in your head a lot. So it's a pretty daunting problem, but I think if you go through it, you will eventually get a good understanding of it. All right. Now let me look at the problems we have left. I didn't expect it to take this long. I don't think I won't be able to go through all of the problems. I'll go through maybe a couple more. I'll go through 14 and 15, the next two, because they aren't terrible. 15 is pretty interesting and kind of involved. It's not as long as this one though. So I'm going to go through the next two problems, 14 and 15, and then I'll wrap up. So 14 is a bit of a breather. Okay, 14 isn't terrible. 14 is kind of more of a classic induction inequality problem, but it's still a bit tricky. So you want to prove that 3 to the n is greater than or equal to n cubed for all positive integers n. Now, on an intuitive level, if you know about behavior of growth of functions, 3 to the n, or if you're in CS, okay, big O notation, 3 to the n is an exponential function. Exponential functions grow way faster than polynomial functions. Okay, polynomial n cubed, that grows pretty fast, but exponential functions grow a lot faster. It's like a whole nother the way that an exponential function grows is completely different than the way that a polynomial will grow. So with that in mind, I think on an intuitive level, this isn't too difficult because 3 to the n will eventually get just absolutely massive. And this will just be true. As long as it's true on the earlier levels are where it could more easily become screwed up. Okay, P of 1. All right, P of 1 is some absolute cake. Okay, thank God. 3 to the 1 greater than or equal to 1 cubed. 3 is greater than or equal to 1. Boom, true. Easy, okay? Now, we're going to assume P of k. and we want to show P of k plus 1. Okay. So again, strategy is we're going to think about k plus 1 cubed. So we want to show that k plus 1 cubed is less than or equal to 3 to the k plus 1. We know k cubed is less than or equal to 3 to the k. So we want to express k plus 1 cubed in terms of k cubed, 3 to the k plus 1 in terms of 3 to the k. We get some extra terms going on, but hopefully we can show that those extra terms make everything work, like everything still works out. So first thing I'm going to do is k plus 1 cubed. I'm going to expand that out because I'm going to get a k cubed term when I expand that out. So that's going to be equal to, so here what I'm doing is starting at k plus 1 cubed. Okay, expanding it out. This is binomial theorem. You could FOIL it, binomial theorem, or just know that when you cube things like k plus 1 cubed, this is the expansion of it. That's something good to know. Now, we know that this term here is greater than or equal to 3 to the k. Okay. So what we can try to do, less than or equal to. Also note, expressing 3 to the k plus 1 and in terms of 3 to the k, 3 to the k plus 1 is equal to 3 times 3 to the k. Okay. So we also got a lot of threes going on here, and we also have so we want to show that this whole thing is less than 3 to the k plus 1. So what we can do is there's these 3 terms going on here, right? These 3 terms. And we know that one of them is less than or equal to 3 to the k. So if we can show that this one is less than or equal to 3 to the k and this one's less than or equal to 3 to the k, then we know that their sum, or wait, you need to show that, so let me look at my work for this. Oh, so if you can show that this is less than 3 to the k and this is less than 3 to the k, then you'll be good in solving this problem. So what we want to show as an auxiliary statement, again, it doesn't have to be true, but it's a good auxiliary statement to consider, is that 3k squared is less than or equal to 3 to the k, or is less than, and there's a reason I say less than, okay, and I'll explain that in a sec. And 3k is less than 3 to the k as well. Okay, the reason I say less than is because if it was less than or equal to in every case, then the issue is there's this plus 1 on the end. So you could imagine a scenario where each of them is 3 to the k, but they sum to 3 to the k plus 1 and then plus 1, and that could mess things up. But if it's strictly less than, then when we add 1, because we're dealing with integers, if you have a is less than b, then you know that a is less than or equal to b minus 1. So you can account for that 1 going on there. So to show this one, okay, we can let's see, how can we show this one? Actually, there's a way I did this quite quickly, if I remember correctly. Let me take a look. So, yeah. Oh, right. Okay. So we know that k cubed is less than or equal to 3 to the k. Right? So we know that k cubed is less than or equal to 3 to the k. Oh my God, that's completely glared out. But no, less than equal to. Oh, wait, what? Yeah. So what we can try to show is that 3k squared is less than k cubed, and then that's less than or equal to 3 to the k, right? So we want to show that 3k squared is less than k cubed because that's less than or equal to 3 to the k, and that gives us this first inequality. Now, this is only true if k is greater than 3. Okay, just divide by k squared. So for k larger than 3, we can pretty directly show that this is true for k bigger than 3. Okay. Then for then for the second one, right? We kind of like a really quick way to show the second one, okay, is that you know that 3k for k bigger than 3, 3k is less than 3k squared, and that's less than 3 to the k. So, like, for k bigger than 3, the second one also has to be true. Okay. So what we've done is we've shown for k bigger than 3, this is less than 3 to the k, this is less than 3 to the k, and then like you can from there prove that this is true for k bigger than 3. Okay, like yeah. So for k bigger than 3, if p of k is true, then p of k plus 1 is true. Now, this is like a common thing in induction. Sometimes you're not always able to completely relate things, I guess. Yeah. It's not a big deal that we haven't shown it for, so we've only shown it for k bigger than 3. It's not a big deal that we haven't shown it for k equals 1, 2, and 3, because that's a super easy thing we can just plug in and check. Okay. There are ways to go about this a little more to get to not just test cases, like at the very k1 equals 2, 1 equals 2, k equals 1, k equals 2, k equals to 3. There are ways to do this where you don't just have to check those cases, but I mean, screw it. It's like super easy to check those cases, and we've shown this is bigger than k bigger than 3, so we'll be good. So all we need to do, all that's left is we need to show that p of that for k equal to 1, k equal to 2, and k equal to 3, right? That these things are true. Okay, and I guess actually, because this is k bigger than 3, wait, yeah, and I think also k equal to 4, because so what we're doing is we're saying that if p of k is true, then p of k plus 1 is true if k is bigger than 3, okay, or if k is bigger than or equal to 4, or no, yeah. So what we need to do is show that so like our base case is now k equal to 4, basically. That's our base case. And so we just need to explicitly check k equal to 1, 2, 3, and 4. So 3 to the 1 is greater than or equal to 1 cubed. Check. 3 squared is greater than or equal to 2 cubed. Check. Okay, 9 bigger than 8. 3 cubed is greater than or equal to 3 cubed. Okay, check. And 3 to the 4th greater than or equal to 4 cubed. That's 81 and 64. Check. Like I said, there's like a more efficient way to go about this, but you know, I've been going for like an hour and 40 minutes, so I'm a little brain dead. I know that wasn't the best explanation, but it demonstrates that that in certain induction problems, especially like the easier the induction problem, you can kind of like you can just where it's easy to check early cases. You can just make your base case like some like k equal to 6, and then just show manually that from k equal to 1 to 6 everything works out. You don't always have to like thread the needle to make all these inequalities work perfectly. Like as long as you can show that it works for some point, and you can show everything below, then you're fine. Okay. All right. I know this is a marathon right here, okay? But we're on the last problem. Last problem, number 15. It's different than all the other ones, okay? So this is gonna be like super interesting, okay? I promise. Actually, this is when I first learned this, kind of blew my mind a little bit, okay? Now, before we even get into the problem, I'm gonna explain a way that you can approximate factorials. Okay, so like a n factorial, there's a way that you can approximate it and the formula you use to approximate it seems totally out of left field. Okay, well, no, like at least if I show it to you. Okay, the formula is that as n increases, as n tends to infinity. Okay, so limit as n tends to infinity of n factorial equals. Keep in mind, n factorial at its heart is like it's like a combinatorics quantity. It's the number of ways to arrange n objects, right? But as n tends to infinity, this equals, I mean, obviously it tends to infinity, but I guess this approaches, or it's similar to the square root of 2 pi n, okay, times n over e to the n. Okay, I'm not even lying. Okay, that's true. You could plug it into your calculator actually and show it, or experimentally. Now, if you've never seen this before, this should be totally bizarre. Okay, and I'm gonna explain kind of how you get this, and it will apply to the next problem that we do. This is called Stirling's approximation. Okay, and if you actually graph n factorial and you graph this like kind of weird looking equation, exponential thing going on, you will see that the graphs actually line up, or they never perfectly line up, because this is like an e, right? I mean, like, this is irrational, but like they get close. Now, what I'm going to do is I'm going to look at the natural log of n factorial. Oh my God, the glare. The natural log of n factorial. Now, that is a wacky, yes, indeed. The natural log of n factorial. Now, this is equal to the natural log 1 times 2 times up to n, right? And if we use the log of a product of numbers is the sum of the logs. So this is equal to ln of 1 plus ln of 2 plus ln of 3 up to ln of n. And actually, this is a kind of, I don't want to say common technique. It doesn't come up that often. But whenever you have like a massive product of things, it can often be useful to take the natural log, or I mean any log, I guess, but ln is like the easiest. It's often useful to take a log, because what it allows you to do is take this product and to rewrite it as a sum. And comparing sums is a lot easier than comparing products. The reason is because there's a lot of techniques, like if you've taken Calc 2, there's all these techniques like for convergence and divergence of sums, and you can also like bound sums kind of easily. And the reason, like in this case, this should like the reason it's useful in this case, which I'm kind of foreshadowing, is that you have like 1, 2, 3, 4 up to n. You have this very sequential nature, right? These terms. So you can it allows you, there's certain strategies you can use to bound a sum like this. Now, the strategy I'm going to use is called the integral comparison test. Okay, I don't know if that's exactly what it is, but what you can do is you can actually you can think of this sum as a Riemann sum. So what you do is you look at the graph of the natural log function. Okay, so this is y equal to ln of x. Comes up here, and it levels out like this. So what we're going to do is we're going to think of this sum as a Riemann sum, which approximates the integral under the integral of y equal to ln x. Okay, so what's interesting here, so because ln x is an increasing function, that means try to revive that math. What is it? That Calc 2 knowledge. Okay, if it's you have an increasing function, the left-hand Riemann sum will always be an underestimate, and the right-hand Riemann sum will always be an overestimate. Okay, because the right endpoints will always be higher than the left endpoints, right? Or the right endpoints will always be higher than the graph. Okay, so if we think of this as a left-hand Riemann sum, okay, so what we do is we're going up to n. Okay, so here's n, and so we have ln of 1. So that's just like a little, I mean, it has 0 height. Okay, so it's like, it would just be like this. Then you have, so this here is 1, this is 2, this is 3, 4, da, da, da. This is n minus 1. And then, so 2, so this, okay, just doing that Riemann sum. So eventually we get this. Oh, I guess we would go, hold up. I guess we would, so we go up to n plus 1, actually. Yeah. Okay. So this here, if you think about the area under the curve here, it's going to be, well, ln1 is 0, so that's not going to matter. Okay. Then this here, so it's interval of length 1, right? The area here is ln2, because we're using, this is ln of 2 on the graph. Okay. Then this is ln of 3. This is ln of 4. Okay. Right. And then all the way up to this final rectangle is of area ln of n. And the reason I knew that that was n plus 1 was because if we're using the left sum, we need to go all the way up to n plus 1 so that the last rectangle has height ln n, because we're doing left hand. So what this tells us is that ln of 1 plus ln of 2 plus blah, 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 up to ln of n is less than, okay, the integral from 1 to n plus 1 of ln of x dx. Okay, so that allows us to bound the sum of ln's, and actually it allows us to bound n factorial because we can exponentiate both sides. That will happen later. Next, what we can do is think of this sum as a right-handed Riemann sum. Okay, so what we do next, let me just redo this. Okay, right-handed Riemann sum. So here we're only going to go up to n, okay, because the last rectangle will have height ln of n. So 1, okay, again, the 1, don't worry about the 1 is a bit weird, but don't worry about it. 2n minus 1. So here we use the right endpoint. So this rectangle here, this here has area ln2. Okay. Then this here is ln3, ln4. Okay. And then we keep going. And this final rectangle has height ln of n, or has area ln n. So what this tells us is that, again, the ln of 1 is not in this picture, but it's just 0, okay? It tells us that ln2 plus ln3, the sum of the ln's is actually going to be greater than the integral from 1 to just n, okay? So this is less than the integral. Oh, that's in the glare, though. It's not. 1 to n of ln x dx. Okay? So we've completely bounded this sum. Okay? And actually, you can, the integral of ln x dx is equal to x ln x minus x plus c. Now, you can get this, I think, by integration by parts or something. Or if you want to convince yourself of this, just differentiate this side and you'll see that it works out. Okay. So what we can do is we can actually evaluate these integrals. Okay. So let's do that. Integral from 1 to n, that's just going to be x ln x minus x evaluated at 1 to n less than, I'm just going to write a big fat sum for that. And this is going to be x ln x minus x from 1 to n plus 1. Then you plug in, you get n ln n minus n, and then plus 1. Okay. Again, this is just algebra. You can do this. And this is n plus 1 ln of n plus 1 minus n plus 1, and then plus 1, so just minus n. Okay. Now as n tends to infinity, okay, this left side and this right side, they're going to get massive. Okay, there's going to be some big numbers. But in reality, like compared to, so if you look at the difference between these two sides, okay, now as n tends to infinity, ln of n and ln of n plus 1 will get very, very close to each other. Okay, because like adding 1 to ln of like a million is like not going to change. Like ln of a million and 1 is not very different at all than ln of a million. So if you think of this as just like an ln n, okay, right? This is just like an ln n. Then the only difference between the left and the right side is that this is n plus 1 ln n, and this is n ln n, okay? So the only difference is like an extra ln n term, okay? I'm speaking kind of nebulously here, but like I'm not approximately. So, but these grow also approximately like a function that the left side grows with is like x ln x, right? I guess minus x. But again, as n to like it's like x ln x minus x, and the only difference is like a single ln term. The whole point, okay, I know I'm kind of going on. The whole point is that these two sides will get closer together in terms of their in terms of proportion. Okay, so what that means is that this sum will tend closer to this left side. Okay, it's like squeeze theorem, like kind of, okay, but it's a bit more abstract. The gist of it is that ln of 1 plus ln of 2 up to ln of n will approximately equal n ln n minus n plus 1 as n tends to infinity. And then when you exponentiate both sides, if I do e to this side, that's just going to be n factorial, because you get e to the ln 1 plus ln 2 plus ln 3, and then you get e to the ln 1, e to the ln 2, e to the ln 3. That's just 1 times 2 times 3, just natural log properties. So that's going to be n factorial is going to approximately equal, if I exponentiate this side, e to the n ln n, that's going to be e to the ln n is just n, right? So that's going to be n to the n, okay? N to the n. Actually, wait, let me just write this out. So that's going to be okay. So n factorial is approximately equal to e to the n ln n minus n plus 1. And actually, there's I guess I kind of omitted something. Okay, there's going to be I'm not going to explain it entirely, but there's going to be an extra like little function of n. Like I said, these don't actually approximately equal. Like, there's going to be an extra little term that is like the difference, and I'm not going to get into that right now. I'm just kind of trying to finish this up. So n factorial will approximately equal e to the ln n minus n, and then this 1 plus f of n. This is going to be like a constant, okay? Because when you do like, or I guess I'll just write it out. So this is going to be like some constant c, okay? And so this is equal to e to the n ln n. So e to the n ln n so this is going to be e to the n ln n over e to the n. And then there's going to be like this big, like there's going to be this e to the c that comes out the front, this constant that's in the front. Oh my God, the glare. And then this is equal to this big constant, e to the n ln n is just n to the n. And this is e to the n. And so this is equal to c times n over e to the n. Okay? So I know I didn't, and it turns out this constant is the square root of 2 pi n. I actually don't completely know why. I could look into it. But the point of this whole explanation is to show you something kind of bizarre, okay? Hopefully explain why n factorial is proportional roughly to n over e to the n, okay? And also this whole integral bounding thing. You can bound sums that have a sequential nature using an integral. Okay. And I like using the natural log as like a good example of that. Okay. So, now we're already almost 2 hours, so I'm going to pick an easier problem to wrap up with. I will go over these problems later at some point. The number 15 takes a while. I'm kind of tired, and but number 16 is is quicker. So I'll do number 16 now. Number 16, we're going to implement the same idea of bounding a sum with an integral. So we want to show that 1 plus 1 over 2 cubed. Actually, we don't even need to use induction here. So the sum of cubes, so 1 over n cubed, is less than 3 halves. Okay? So what we're going to want to do is think about the function 1 over x cubed. Okay? 1 over x cubed is a decreasing function. So any left-handed Riemann sum will overestimate the function. Any right-handed Riemann sum will underestimate the function, the integral. Sorry. So we can think about this sum here as a Riemann sum, okay, of y equal to 1 over x cubed. And if we do that, now again, we want to show that this is less than, we're trying to show that this is less than something, is less than something, is less than something, is less than 3 halves. So we want to bound this above. We want to find an upper bound for this. So we want to think of it as, you think about it, we want to think of it as a right-handed Riemann sum. Okay. So here's 1. Okay. Here's 1, 2, 3, and then you can go all the way up to n or n minus 1 or n plus 1 or something like that. So what we're going to do, actually, let me. Now here's a bit of a problem. Okay, so here's like one way you could go about this kind of directly. Let me make sure that what I'm saying is true. Is true though. Almost there. My work is, all my papers are going everywhere. Okay, yeah. So yeah, so if you wanted this, like, if you just like try to go at this the same way we went last time, so you try to think of this as the left-handed Riemann sum of, so here's 1, okay, this here has area 1 over 2 cubed, then you go up to, the final one is going to have area, so you want to go up to 1 over n, the final one will have area 1 over n cubed. Okay? And so you've bounded this sum by an integral. But here's the problem. What is that integral? The integral is the integral from 0 to n. But 1 over x cubed, the integral from 0 to n, that diverges. That's infinity. So so we showed that this sum is less than infinity, which is not very helpful, okay? Because everything's less than infinity. So we can't go at this directly using the same way. What we can do instead is, so the problem is happening at 0. The problem is that we're integrating starting at 0. So what we can do is integrate starting at 2 and just add 1. So we have, this 1 is still here. So we can instead bound this. So as 1 plus, so the 1 we just carry over, and then we use the integral from 1 to n of 1 over x cubed. Okay, that's how we can fix that issue. Then this integral, okay, remember your integrals from Calc 2, 1 over x cubed, the integral 1 over x cubed is minus 1 over 3x squared. Wait, hold up. No, minus 1 over 2x squared. So this is equal to 1 plus, I guess it'd be 1 minus 1 over 2x squared evaluated at 1 and n. Okay. This is equal to 1 minus 1 over 2n squared minus or plus a half. And that's equal to 3/2 minus 1 over 2n squared. And so we've shown that this sum is always less than this integral, and that integral always evaluates to 3/2 minus 1 over 2n squared. So no matter how big n is, right, 3/2 minus 1 over 2n squared will always be less than 3/2, and so that proves the statement. That's not even an induction problem. I bet the solution in the book probably uses a different solution. It probably uses the sum, but I really like this whole integral thing because I just think it's really useful to be able to bound sums using an integral, because you can evaluate integrals, and you don't get a lot of, you have this big sum and you're able to bound it by a expression which is only a few terms, right? It's only minus 1 over 2n squared plus a half, right? Okay, thank you. Thank you for sticking with me for 2 hours and 5 minutes. If I went through all the problems, we'd probably be here for 4 hours. So I'm not about to do that. I hope that was informative. And I know we only went through 5 problems and it was 2 hours, but I mean, that's kind of how it is. A lot of these problems, they're very challenging. They take a while and you have to really sit and think about them. And see, that was just the explanation. That was me explaining it. Okay. Me working on it is working 3 times slower. Okay. So, but it's definitely useful to, it's very important. It's a good way to become a better problem solver and just to become a more patient person. Okay. You have to have a lot of patience to be able to work on these problems, but because they take so long and because they're hard, when you are able to solve them, it makes it all the more satisfying. And that feeling can often be pretty priceless. So like I said, thanks for sticking with me this whole time. Make sure to smash that like button, comment, and subscribe. And hope you have a good day.